We are going to do some function analysis on a variety of functions where we will determine the domain, whether or not there are holes, x-intercepts, y-intercepts, vertical asymptotes, and horizontal asymptotes. Are there any points of discontinuity? And what is the symmetry? So let's start with problem number 10. The domain. The domain depends on whether or not you have any holes or vertical asymptotes. So before I look at what the domain is, I'm going to start by figuring out are there any vertical asymptotes and are there any holes? Then I'll come back to the domain. To answer that question, it's helpful to write this function in factored form. I'm noticing that I can factor the denominator as x plus 2 and x minus 2. All right, and the numerator is x minus 2. Writing in factored form is so important because holes happen when a factor cancels out. So in factored form, you can see that we have these two factors that are the same in the numerator and the denominator. This is going to lead to a hole. So there's going to be a hole. Exactly where it is depends on setting either one of these equal to 0. If I set x minus 2 equal to 0 and solve, that will give me x equal 2. That tells me where my hole is. So there's a hole at 2 comma something. All right, and of course I got the 2 from right there. But I need to know what the y value is that goes with the 2. And for that, let's go ahead and cancel out the x minus 2 factor. So after we remove the hole, then that's going to leave us with 1 over x plus 2. And this is what we will use to figure out what the y value is. So if we plug in if we plug in 2 for x, that's going to be 1 over 4. So that's why there will be a hole at 2 comma 1/4. All right, so that's going to help me with my domain in a moment. Now, vertical asymptotes. You get the vertical asymptotes by setting the denominator equal to 0. All right, so when I ask myself what the vertical asymptotes are, I set the denominator equal to 0. If I set this equal to 0, that's going to give me x equals negative 2. So that is my vertical asymptote. I have a vertical asymptote at x equals negative 2. Now, the domain is going to be all real numbers except for the hole. We're talking about the x value here, so I'm just talking about the 2. So except for the 2 and the negative 2, the hole and the vertical asymptote. So as I construct my domain, if it weren't for the hole and the vertical asymptote, the domain would just be negative infinity to positive infinity. So I just need to skip over negative 2 and I need to skip over positive 2. Okay, so the way I can do that is, so this is what negative infinity to positive infinity looks like. Okay, but I don't have an unbroken domain. I have a vertical asymptote at negative 2. All right, so I need to skip over negative 2 for that reason. And then I have a hole at x equals positive 2. So I need to skip over that value as well when I'm describing my domain. So I'm going to skip over negative 2 and I'm going to skip over positive 2. So I'm going to wind up splitting the domain into 3 different parts. So I don't get to say negative infinity to positive infinity. Instead, I will say, let's see, can I squeeze it all in here? No, I'm going to let it stretch over this way. I'm going to say from negative infinity to negative 2. All right, that's this first section. And then I'm going to say from negative 2 to positive 2. So I'll say union negative 2 to positive 2. And I'm going to skip over positive 2, and then I'll say from 2 to infinity. That's how you say the domain, but you're basically just skipping over any vertical asymptotes or any holes. You just have to skip them. All right, moving on to the x-intercepts. If you want to find the x-intercept, you let y equal 0. In other words, you let the entire function, you set the entire function equal to 0. Well, remembering that the denominator can't be 0, because that would be undefined. The only way that the whole function is going to equal 0 is if the numerator equals 0. Okay, this is the only way that the entire function is going to equal 0, is if x minus 2 is equal to 0. So you can basically set the numerator equal to 0. Okay, if I solve that, that's going to give me x equals 2. All right, so that's going to be 2 comma 0. An intercept is an ordered pair. So I just found from this, I got that x is equal to 2. So that's why I put an x value of 2. But the y value, of course, will be 0 because it's where the graph touches the x-axis. But don't just put 2, put 2 comma 0. If you want to find the y-intercept, you let x equal 0. All right, so I'm just going to clean this up a little bit. So if I want to find the y-intercept, I'm going to let all of the x values equal 0. So that's just going to leave me with this part, which reduces down to positive 1/2. So 0 comma 1/2. I let x equal 0. So there's my x equals 0, and the y value turns out to be 1/2. Again, don't just put 1/2. An intercept is an ordered pair. Put 0 comma 1/2. Okay, let's talk about horizontal asymptotes next. Well, horizontal asymptotes are going to come from the end behavior. So a nice way to think of this is the fact that if you look at the numerator, only one of these terms is actually going to matter. As x gets bigger and bigger and bigger, only this is going to matter. Because this will be 1,000,000 and this will be minus 2. 1,000,000 minus 2 is basically 1,000,000. And the same thing here. This minus 4 is not going to matter as we approach infinity. So as we approach infinity, the only part that will matter is x squared over x. So this function will approach, so I'm going to say f of x is going to approach x over x squared as x gets bigger and bigger. But this reduces down to 1 over x. So now what does this approach as x gets bigger and bigger and bigger? So as you go 1 over 10, 1 over 100, 1 over 1,000, the value of this fraction is getting smaller and smaller and smaller. It is approaching 0. So that's why this is going to be the horizontal asymptote. The horizontal asymptote is basically the end behavior. All right, if the end behavior is a constant, if you have a number here like 0 or 1 or 5, then that's going to give you your end behavior. So y equals 0. If this is infinity or negative infinity, then that means there is no horizontal asymptote. Okay, let's talk about continuity. Well, you can see by the domain that we have some discontinuity in here. A discontinuity is going to be a break in the function somewhere. Okay, it's going to be some sort of a break in the function. So this function is definitely not continuous because we have a hole at 2 and we have an asymptote at -2. Now we've learned that a hole is called a removable discontinuity. So we can say there is a removable, all right, and it's understood that I'm saying removable discontinuity. There's going to be a removable discontinuity at x equals 2, all right? We just name the location according to the x value. We learned that an asymptote is an infinite discontinuity. So this vertical asymptote is also splitting the graph. So we're going to say that there is an infinite discontinuity. Just going to squeeze this in here. At x equals -2. Okay, so our holes and our asymptotes give us discontinuities, right? Removable and infinite. We have a third type of discontinuity called a jump. For that to happen, we really need some type of a piecewise function where we have two different domains, and maybe we have x plus 2 for x is less than -1, and then we'll have 2x squared if x is greater than or equal to -1. It really takes a piecewise function to create that jump discontinuity. Symmetry. All right, what about symmetry? We've learned about two kinds of symmetry. We have even symmetry is when a function is symmetric around the y-axis. So this would be an example of even symmetry. And then there's odd symmetry, which is a rotational symmetry. All right, it has to be centered around the origin. The classic example of odd symmetry is our cubic function, x to the third power is what I'm basically drawing right now. And if I rotated this around the origin and turned it upside down, it would still look exactly the same. That's what odd symmetry is. It's rotational symmetry around the origin. At a glance, I can tell that this function is going to have neither symmetry. I'm going to put none. Now think about it. We have one vertical asymptote at x equals -2. So think about what that does as far as even symmetry. If I have one vertical asymptote and it's over here to the left, all right, it's at -2. So here I have a vertical asymptote. No matter what else is going on, there's no way that the graph is going to be symmetric. To even have a shot at it, this asymptote had to be at the y-axis. So then maybe, depending on whatever else is going on, maybe it could be symmetric. But the way it is, being off to the left, there's no way it's going to have y-axis symmetry. This also really ruins the rotational symmetry. Because if I turn this upside down, just with this alone, I don't even have to worry about the rest of it. Just because of this asymptote that I have in here. If I rotated this picture upside down, the asymptote would go from being on the left to being on the right. So there's no way it's going to look the same when I turn this upside down. So there will be no symmetry. Okay, problem number 11 is going to be a little bit more straightforward. This is just a polynomial. There's no denominator or anything. So there are no undefined values. There will be no vertical asymptotes. There will be no holes. There's just nothing strange going on. So the domain is going to be negative infinity to positive infinity. All right, there are no holes, and there are no asymptotes. Wow, they didn't even give me a spot to write holes. Okay. Never mind. So the domain will be negative infinity to positive infinity. The range will also be negative infinity to positive infinity. So as we are writing the domain and range, we are leaning on the fact that we know what the parent function looks like. The parent function is x to the third power, and we know that that looks like this. And we know that multiplying by 8 is just a vertical stretch. So if you just stretch this vertically, it's still going to have the same basic shape to it. So that gives you the domain. It goes left and right forever. It goes down and up forever. So there's your domain and range right there. But that will also give you the x-intercept and y-intercept. Because like the parent function, the x and y-intercept will be the origin. So we're going to have 0, 0, and 0, 0. This will also help us with our increasing and decreasing intervals. As I travel from left to right across this graph, notice that I'm going uphill the entire way. So the entire graph is increasing. In other words, the entire domain is increasing. So it is increasing from negative infinity to positive infinity. There are no decreasing intervals, so I'm just going to say none. As far as continuity, I'm going to say this is continuous because there are no breaks in the graph. There are no gaps, there are no jumps, there are no asymptotes. It is continuous. For symmetry, this is the classic example of odd symmetry, the rotational symmetry. If I rotate this around the origin, if I turn it upside down, it's still going to look exactly the same. All right, problem number 12. Oh, back to denominators, back to having asymptotes. All right, do they ask me? All right, so I'm looking for the domain. So once again, before I say what the domain is, I'm going to first figure out what the holes are, if any, and I'm going to figure out what the vertical asymptotes are. All right, because the domain is just all real numbers except for holes and asymptotes. I just have to skip over these two things when I write the domain. Okay, so this will factor a tiny bit. So this will be the same thing as 2 times x minus 3 over x plus 5. Now, this doesn't really do anything for us because the nothing cancels out. So there's really no point in that, except for it tells me that there are no holes, because holes happen when you have a factor that cancels out. Like if I had x minus 3 and another x minus 3, that would give me a hole at x equals positive 3. So I'm just going to erase that because I didn't learn anything from it. For vertical asymptotes, you get vertical asymptotes by setting the denominator equal to 0. So if I set x plus 5 equal to 0, all right, I'm taking my denominator, that's going to give me my vertical asymptotes, because this will be x equals negative 5, and that is my vertical asymptote. There were no holes. I have a vertical asymptote at negative 5. So that means when I do my domain, I just need to skip over -5 because there's a vertical asymptote there. Okay, so that means my domain will be from -infinity to -5. Union -5 to infinity. All right, it's the left part and then the right part. I just have to carefully skip over the -5. All right, what else? I need my x-intercept. If I want the x-intercept, you let y equal 0. Okay, that means the f of x is going to be 0. But the only way that the whole function is going to equal 0 is if the numerator is equal to 0. All right, when you have a fraction like this, both of these things mean the same thing. Setting the entire function equal to 0 means that the numerator has to be equal to 0. So 2x minus 6 has to equal 0. All right? Because the denominator can't be 0. So the only way that the entire function is going to be 0 is if the numerator turns out to be 0. Adding 6 to both sides, I have 2x equals 6. Dividing by 2, I have x equals 3. Okay? Remember, for the x-intercept, I let y equal 0. So I'm going to have something, comma, 0. And the x turned out to be 3. Please put 3, comma, 0. Don't just put 3. An intercept is an ordered pair. If I want the y-intercept, I'm going to let x equal 0. All right, so I need to clean this up a little bit to show you what that looks like. If I let x equal 0, that means I'm putting in zeros for all the x's, like here and here. Well, that's going to wipe out this whole term. So that's just going to leave me with -6 over -5. So that's really 6/5, positive 6 over 5. So the y-intercept, I let x equal 0, so I'm going to have 0, comma, 6/5. And that's the y-intercept. The horizontal asymptote, if there is one, is going to come from the end behavior of this function as x approaches infinity. Okay, so let's check it out. Horizontal asymptote. Now, the end behavior, as x approaches infinity, the -6 and the 5 will become irrelevant. So the 2x and the x will grow while the -6 and the 5 stay constant. So as x gets bigger and bigger, these the -6 and the -5 won't matter. So as we talk about the end behavior, we will say that the function approaches 2x over x, okay, just looking at the part that matters. But that simplifies down to 2, right? Because like at that point, the x's will cancel out and you just have 2. So that tells you that your horizontal asymptote is going to be y equals 2. Anytime this turns out to be a constant, like 2 or 0, that's a horizontal asymptote. If this were infinity, then we would say there is no horizontal asymptote. Okay, so that's it for number 12. Moving on. All right, last one, number 13. Domain. So once again, before we talk about domain, we should first talk about holes and vertical asymptotes, because the domain is just all of the x values except the holes and vertical asymptotes. All right, in order to see whether or not there are any holes, I really should factor the numerator. So in the denominator, I have x minus 4. I'm going to factor the numerator because I'm betting it does factor. X squared of course, is x times x, 6. 6 could either be 6 times 1 or 2 times 3. Looking at the fact that I have a middle term of 1, I'm betting that the 2 times 3 is going to work. To get a positive 1, I'm going to need a positive 3 and a negative 2. So I'm going to need a negative 2 and a positive 3. Luckily, that gives me negative 2 times positive 3 is negative 6, which is what I wanted. So this is how you factor it. Nothing cancels out. I don't have any factors that are the same. If one of these had been x minus 4, that would cancel the x minus 4. That would give me a whole at x equals 4. But as it is, there are no holes, so I'm just going to say none. Now, vertical asymptotes come from setting the denominator equal to 0. Set the denominator equal to 0. So if I set x minus 4 equal to 0 and solve, that's going to give me x equals positive 4. That's my vertical asymptote. So now I can talk to you about the domain. There were no holes, but there is a vertical asymptote. So the domain is just all of the x values, except I need to carefully skip over the vertical asymptote. So that's why the domain will be negative infinity to 4, and then 4 to infinity. So negative infinity to 4 union, all right, don't just put a comma, and then 4 to infinity. All right, of course I'm using parentheses around the 4 because the 4 cannot be included in the domain because it is an asymptote. Okay, let's talk about x-intercepts. For the x-intercepts, you let y equal 0. If you've got a fraction, so letting y equal 0 means setting the entire function equal to 0, because f of x is y. There's only one way that the entire function can possibly equal 0, and that's if the numerator equals 0. The denominator can't be 0. Okay, so the only way for the whole function to be 0 is if the numerator equals 0. All right, so sure, we let y equal 0, but another way to think of that is set the numerator equal to 0. So if I set the numerator equal to 0, I'm going to have two solutions because I'm really going to wind up setting each of these equal to 0. So that's going to give me an x value of 2, all right, by setting this equal to 0. And it's going to give me an x value of negative 3. Okay, because of setting x plus 3 equal to 0. The y value, of course, is 0. All right, so for x-intercepts, they must be ordered pairs. Don't just put 2 and negative 3. Put 2, 0 and negative 3, 0. For the y-intercept, you let x equal 0. So when I say let x equal 0, I mean substitute 0 for all the x's. All right, so that is just going to only leave this part behind. A negative divided by a negative is a positive, and 6 over 4 reduces down to 3 over 2. So this is going to give me 0, 3 over 2. Don't just put 3 over 2. An intercept is an ordered pair. Last, let's talk about the horizontal asymptote. Okay, if there is a horizontal asymptote, it'll come from the end behavior. If the end behavior is a constant, then that'll be your horizontal asymptote. Now, the end behavior is all about what happens to the function as x approaches infinity or negative infinity. So we have learned that when you have more than one term, like we've got this trinomial up here, as x approaches infinity, the term with the highest power is going to grow so much faster than the other terms that eventually the other terms will become insignificant. So only the x squared is going to matter, and in the denominator, only the x is going to matter. So just ignore the rest of it. So we see that as x approaches infinity, the function is approaching x squared over x. But then that would simplify down to x, because one of the x's will cancel out. And of course, as x approaches infinity, okay? I mean, duh, right? So this is not a constant, all right? X just gets bigger and bigger and bigger. It just approaches infinity. So this would mean that the graph just goes up into the air. So that is not an asymptote. So if this had been a constant like 0 or 2, then that would have been the horizontal asymptote. But in this case, we will just say none.